So this workshop 9, a slight mixture of things we'll do today. We're going to start by going back and looking at Cartesian products and giving you a bit of practice in... this question comes from the sheet, more practice with definitions, proofs and examples, so you may have already done it. If you haven't, here's a good one to practice working with definitions of various things. Okay, so Cartesian product, as we saw before, is nothing to do with multiplying numbers. X cross Y means those ordered pairs where the first coordinate is required to be in the first set and the second coordinate is required to be in the second set. So we had a look at this with products of intervals in the real line before. Products of intervals in the real line, you tend to get things like rectangles, squares, that sort of shape in R squared. And nothing circular. So you can get line segments and points as well. And various bits and pieces, made up of bits and pieces like that. Right, so I'll work with subsets of R. This actually, they don't have to be subsets of R. This question is still true. But I just made them subsets of R so that you can visualize it a bit more easily as what's going on. But your proof should be pretty general. And you're required to prove that the left-hand side, which is the Cartesian product of two set differences, is contained in the right-hand side, which is the set difference of the two Cartesian products. Okay? So you also have to remember what the set difference is. E take away F is equal to those X in E such that X is not in F. But perhaps let's not you call it X, because these might actually be vectors here. So we'll call them Z in E such that Z is not in F. But in this question, on the left-hand side, yes, there'll be real numbers involved in the set difference. On the right-hand side, the things you're taking the set difference of are subsets of R squared. So these Zs will be two-dimensional vectors there, two-dimensional points. So slightly different when you're doing the set difference on the right-hand side. Call that left-hand side. Call that right-hand side. And for part A, what you have to do is show that these are sets of ordered pairs, so you have to prove that if x, y is in the left-hand side, then it has to be in the right-hand side. Okay, that's how you prove the left-hand side is a subset of the right-hand side. And then in B, you should draw some pictures and convince yourself that you found some nice... you can do it with a few points, but you might find it nicer to do it with intervals and rectangles and things, just to see what's actually going on here. Right, I'll pause the recording and we'll come around and see how you get on with this. Okay, I'm going to start the recording again. So there are lots of different ways to do this, but let me give you one approach. As I said, what you have to do is prove that if xy is in the left-hand side, then xy is in the right-hand side. You should not try to prove they're equal, because in part B you're going to show that they're often not equal. So it's not necessarily a good idea to try and write down the exact definition of both sides and start manipulating them, because you're not going to be able to prove they're equal when they're not. If you want to prove a subset relation, you should probably go along this way. And the best way to start to prove that xy left-hand side implies xy on the right-hand side is to say let xy be in the left-hand side. Or suppose xy is in the left-hand side. That's the same thing, really. I'll do let. Let xy be on the left-hand side, if there are any, of course. If there aren't any, then it's trivial anyway. Let xy be on the left-hand side. Then by definition, that means that x is in A take away B, and y is in C take away D. So by definition of A take away B cross C take away D, this means x is in A take away B, and y is in C take away D. Now, I don't want to forget that. Let's call that star, because I'm going to come back to it twice. Okay? This means you're in A and you're not in B, and y is in C and not in D. In particular, x is in A and y is in C, so that's a good start. In particular, x is in A and y is in C, so xy is in A cross C. So that's a good start. Okay? We've managed to show that xy is in A cross C, so all we need to do now to get it into the right-hand side is to show it's not in B cross D. Now there's two different reasons why it's not in B cross D. Because to fail to be B cross D, you only need one of the coordinates to be wrong. So there's a bit of overkill here, because we actually know that both of the coordinates are wrong. We actually have x is not in B and y is not in D, but you only need x not in B or y not in D. So I'll give an asymmetrical proof and say, since phi star x is not in B, it doesn't matter whether y is in D or not. xy is definitely already not in B cross D. And you don't care about the fact that y is not in D. That's overkill. Of course, you could have said, since y is not in D, and not care about the fact that it's not in B. But I want to point out where the overkill is here. So, xy is in A cross C and is not in B cross D, so it's in A cross C, take away B cross D, as required. That's the right-hand side. If you're on the left-hand side, then you're in the right-hand side, and so the left-hand side is a subset of the right-hand side. I'll just summarize that. xy in the left-hand side implies xy in the right-hand side. So left-hand side is the subset of the right-hand side. That's what we did. Okay. Now, the reason that they're not equal is because of the overkill bit. Because we only needed one of the coordinates to be wrong. And we actually knew that both of the coordinates were wrong. So that gives you some space to find an example. Let's have the question in front of me. Here we are. Okay, so who thinks that they've got an example with some intervals? Yeah, what have you got?
If you have A to be the real numbers between 2 and 5, B to be the real numbers between 3 and 4, C to be the real numbers between 3 and 6.
Okay, you're going too fast for me. Are we going to be inclusive, by the way?
Yeah.
Okay, so A is going to be 2, 5, did you say?
Yeah.
B?
3, 4.
3, 4. Yeah.
C, 3, 6.
Yeah.
D, 4, 5.
4, 5. Let's see what I can do with that. So we want to look at, so it's A and B are in the first coordinate and C and D are in the second coordinate. So let's draw a picture. So A and B, let's see, 2 and 5 and 3 and 4. So let's have 2, ooh, that's not very good. Let's go back. Let's 2, 3, 4, 5. And the other ones we're going between 3 and 6. So let's start here, 3, 4, 5 and 6. Let's figure out where these sets are. So A is going between 2 and 5. That's A. B is going between 3 and 4. Some more colours. Let's see. C is going between 3 and 6. I don't know what colour that is. And D is going between 4 and 5. So there's D. Right. So A cross B, A cross C is quite big. A cross C is this big thing. This is A cross C. And the other one, the B cross D, is in here. And A take away B cross C take away D gives you the 4 quarter bits. Roughly speaking, though excluding some edges. Does that fit with what you got? Okay. You can see that we're missing those 4 white bits left here are the bits that would have been, they're the things that are in A cross C take away B cross D, but which are not in A take away B cross C take away D. So these are all the overkill ones. These are the ones where one of the coordinates is wrong but not both. Whereas the 4 quarter regions are the ones where both of the coordinates are wrong. Does that make sense? Okay, well, I'll assume that people are happy with that. Anyway, draw some pictures for yourself and see what you get. And I'm sure you can draw better pictures than me. Right, so let's move on to a completely different subject. I want to go back to characteristic functions. I'm going to think this time of my characteristic functions as taking values in the integers. So you could think of the characteristic functions as having codomain with just 2 points, or you can think of them as having a bigger codomain. My characteristic functions here, I'll have a domain, some universal set or other. You can think of it as the real numbers if you like, I don't care. The codomain I'll take to be the integers, which is fine. Just so that I can add them, and it makes sense. Otherwise, it's not obvious what you do. Right, so we've looked at this before. The characteristic function corresponds to the set E. It counts 1 if you're in the set and 0 if you're not in the set. And we know that 2 sets are equal if and only if they've got the same characteristic function. So 2 subsets of X will be the same if and only if they've got the same characteristic function. Because the characteristic function tells you what the set is, and the set tells you what the characteristic function is. Okay. But I'm going to do something slightly different here. I'm going to talk about 2 integer-valued functions and say what does it mean to say they're congruent to each other modulo 2. So this is slightly different from integers being congruent modulo 2 because it's for functions. but it's the same idea. I'll say that the functions are congruent to each other modulo 2 if whichever x you look at in your domain, maybe the real numbers, f of x, when you compare f of x with g of x, not comparing f of x with g of y, we're comparing f of x with g at the same x, the difference should be even. So, for example, so whichever x you look at, either both f of x and g of x should be even, or both f of x and g of x should be odd. But it can move, if you move to different points x in your domain, you're allowed to get different. It could be that they're both even in some places and they're both odd in other places. But you mustn't find any x where one of them is even and the other one is odd. Otherwise, they're not functions that are congruent modulo 2. Okay. So I'm going to let you assume, as a standard fact, that two subsets of x are equal if and only if their characteristic functions are exactly equal. And now I'm going to ask you to check that, in fact, if you take two subsets of x, then the sets are equal if and only if the characteristic functions are congruent modulo 2, which is usually a slightly weaker statement about functions. If two functions are equal, they're definitely congruent modulo 2, because the difference is always naught, which is even. But generally, two functions could be congruent modulo 2, but be completely different. Like one could be the constant function naught, and the other could be the constant function 4. Those would be congruent modulo 4, but with different functions. Why can't that happen if you're dealing with characteristic functions? And the answer is, look at what are the possible values chi a of x minus chi b of x can be. If you're requiring it to be even, what are the possibilities? Okay, so let's let you think about that, and we'll come around and see how you get on. Okay, I'm starting the recording again. Okay, so let's say let x be an x, if there are any. Then chi a of x is in it's 0 or 1, and chi b of x is 0 or 1. So chi a of x minus chi b of x can only be minus 1, 0 or 1. You can just check all the four possibilities, and you get minus 1, 0 or 1. Now, of those, only 0 is even. So, as a result, chi a of x minus chi b of x is even if and only if chi a of x equals chi b of x actually. So this is not true for general integers. For a general integer, if they're equal, then they're equal mod 2. But for values taken by but for things you get of the form characteristic function minus characteristic function, in other words, for things in minus 1, 0 and 1, that's even if and only if it's naught. So that's a special case. Okay. And then, that basically is why. So, if chi a of x minus chi b of x is congruent to naught for all x in x, if and only if chi a of x equals chi b of x for all x in x. Which is the same thing as, that's if and only if chi a equals chi b. Let's have a tiny bit more room for that. Thus, chi a, that's the first one mentioned here is that chi a is congruent to chi b mod 2. That's if and only if they're the same function. Literally. Actually take the same values at everything, which is if and only if a equals b. You don't have to do it that way. There's other things you can do. But that's my suggestion. Any questions about that proof? If not, then what we do for the rest of the session, we're going to assume that it's enough to check whether characteristic functions equal mod 2 in order to figure out whether they're the same set. So now we're going to look at the symmetric difference. The symmetric difference is quite pretty. So here's A, and here's B. And for the symmetric difference, you're allowed to be in A and not in B, or you can be in B and not in A, but you're not allowed to be outside the union, and you're not allowed to be in the intersection. So you get these two pieces. So first definition is A take away B union B take away A. That's the A take away B bit, and the other side is the B take away A bit. As I say, using a Venn diagram, you could also see that it's the same thing as A union B take away A intersection B, because you get everything in A union B except you have to throw out the intersection. So it's the same thing. So I don't mind which of these you think of it as. Those are both the same. Those are the symmetric difference. Now, for case-by-case analysis, you better include the case where you're outside the union. So I'll draw a big box for X as well. When you're doing case-by-case analysis, there are basically 4 places to look. There's outside the union, there's in A but not B, there's in B but not A, there's in the intersection. And that's 4 different cases for your elements of X, which cover all the different possibilities. If you're trying to check whether 2 functions are the same, or congruent modulo 2, it's enough to check those 4 cases separately. So it says here, using case-by-case analysis or otherwise, show that the characteristic function of the symmetric difference is congruent to what you get by adding the 2 characteristic functions mod 2. You see, in a previous lecture, we looked at the union, and we discovered that if you just took the union, usually you don't add the characteristic functions, because the problem was there would be places where you got the value 2. Well, 2 is now the same as 0, so that will still give you something. Okay, so let's let you think about that. Check the 4 cases separately, or do it any way you like about how this works out. Okay, but 4 cases should do it. Okay, let's give you a chance to think about that one. Okay, I've started recording again. Let's just draw that thing again. So here's your X, here's your A, here's your B, and A triangle B with this shaded bit, the symmetric difference. And now we want to see in the 4 cases what values you get. The most interesting one is when you're in the intersection of the 2. Okay? So if X is in A intersection B, then X is in A, X is in B, but X is not in the symmetric difference. So when we look at what these functions do, the characteristic function of the symmetric difference will give you 0. But the characteristic functions of A will give you 1 each. So you get 1 plus 1 equals 2. And fortunately, naught is congruent to 2, so we're okay in that case. For all other places, you actually get exact equality rather than just equality modulo 2. If you're in A but not B, then you get 1 equals 1. Same for if you're in B, not A, you get 1 equals 1. And if you're not in either of them, you get 0 equals 0. So you can check the other cases for yourself. So in the other 3 cases, you actually get chi A triangle B of x equals chi A of x plus chi B of x. And since they're equal, they're definitely congruent modulo 2. So that works. You can also use the notion of exclusive OR. If you don't want to add modulo 2, you can do exclusive OR, which is exactly the same. The advantage of adding modulo 2 is that it's associative. You might be more familiar with the fact that that's going to be associative and distributive and everything, because we did the various things about how the arithmetic worked with congruent modulo 2. So I don't think you're going to have time to do this, so let me sketch why question 4 works. Some of you may have already done it. It says using congruence of characteristic functions modulo 2 or otherwise. Now, I have to tell you, if you can do it with Venn diagrams, and it's not bad if you get it right. They're quite pretty Venn diagrams you get. If you try and do it with set operations and distributivity and associativity and directly with set operations, it is absolutely horrible. I strongly do not recommend that you try and do this directly using the set operations, because it's really ugly. Maybe the second one's not as bad. The second one's not too bad, but the first one is really horrible. But if you do it with characteristic functions, it really drops out very nicely, because the characteristic function of A triangle B triangle C is congruent to the characteristic function of A plus the characteristic function of B triangle C mod 2, which is congruent to the characteristic function of A plus the characteristic function of B plus the characteristic function of C mod 2. But that's equal to the characteristic function of A plus the characteristic function of B plus the characteristic function of C, because that's what you get when you add functions, which is congruent to the characteristic function of A triangle B plus the characteristic function of C mod 2, which is congruent to the characteristic function of A triangle B triangle C mod 2. These two characteristic functions are congruent mod 2, so the sets are the same. And the other one works because when you do intersections, you're doing multiplication. So NB, the second part, the characteristic function of E intersection F is equal to the characteristic function of E times the characteristic function of F. So now you can do it with distributivity as well to get the other one. So that's how you do that. if you want to know what this thing actually is, A triangle B is the set of things which are in exactly one of the two sets. A triangle B triangle C is the set of those things which are either in one of the three sets or in all three of the three sets. And generally, if you take a symmetric difference of lots of them, it's the set of elements which are in an odd number of the relevant sets, in the as long as you count it right. So it's either in exactly one of them, or exactly three of them, exactly five of them, or that sort of thing. So that's how it works. Okay, I think that's enough for today, unless there's any questions.